So we've been talking about enthalpies of reactions and identifying enthalpies of reactions from data. Now let's say we have a given reaction and we want to connect that back to bond energy and how bond energy of our reactants and how the bond energy of our products relate back to the overall enthalpy change of the reaction. Now as we're thinking about identifying some information as it corresponds to bond energy, let's use this example reaction here to be able to explain how heat is released when 50 grams of water is formed when we react hydrogen and oxygen gases together. And this is shown in reaction 1. Now we're going to connect this back to bond energy. So now as we're trying to connect it back to bond energy, we know that their enthalpy is negative, meaning we are going to be releasing heat. So we're going to be giving away energy in the form of heat. Now, why are we going to be giving away energy in the form of heat? Well, if we look at these two reactants in our product, we have the hydrogen molecule, H2, so a single bond between hydrogen and hydrogen. And then we have oxygen, O2. And if we were to draw out our Lewis structure, we would notice that it has a double bond. And we'll see why it's important that we focus on differentiating between single or double bonds in a second. Then we have our water molecule, and our water molecule looks something like this. We got a bond between hydrogen and oxygen, and then two lone pairs sitting on our oxygen molecule, oxygen atom. Now we also have the fact that we have two of these, and we have two hydrogen molecules as well. And we're going to see that's going to correspond to our enthalpy change and corresponding back to our change in enthalpy. Now if we look at these two reactants in our product, let's look down at our first table here and think about, for this reaction, how does our bond energy correspond back to our reaction? So here we have the bond energy. So we notice every single one of these bond energies are positive. So they're all positive with regards to those bonds. So when we think about these that are positive, we can think about this as the energy needed to break the bonds that are present here as we're written about. So we notice to break the hydrogen-hydrogen bond, it's going to take us 436 kilojoules of energy to break one of those hydrogen-hydrogen bonds. Again, for a mole of those. Likewise, if we have an oxygen-oxygen double bond here, we see that it's going to take 498 kilojoules for a mole of those oxygen-oxygen bonds. Now, if we have a single bond, we notice that that is much smaller, and that can let us know that is a weaker bond, and the oxygen-oxygen double bond is a stronger bond, which makes sense because they're sharing two pairs of electrons instead of a single pair of electrons. So now that we have these ideas here, we want to go ahead and think about how does these bond energies connect back to our enthalpy change. Now we do that by looking at our overall reaction, and before we can actually even predict possibly what our enthalpy change is for this reaction, we would first have to actually draw out what our molecules look like, and we already have that done here. So we see, before we can do anything, our step one is we have to have diagrams or Lewis structures of all of the reactants and products. And the reason why we have to have diagrams for all of our reactants and products, we need to know what bonds we have present in those reactants and product. Because if we don't know what bonds we have present, we don't know whether it's a single bond between oxygen and oxygen or a double bond, or if we actually have a carbon-hydrogen bond, or if we only have oxygen-hydrogen bonds within a molecule. So it's important for us to know what bonds are present there, because it's going to help us define what bonds are going to be broken and what bonds are going to be formed. So now we want to go ahead and we've diagrammed those. We already have that done here. And then the second step is we need to identify the bonds that are broken, and we can see that's going to be adding in energy to make that happen, and the bonds formed, which is going to be releasing energy as we go ahead and form those new bonds. Now let's go ahead and do that with our reaction here. So if we go back up and we look at our reaction, we notice that we have one hydrogen-hydrogen bond for every hydrogen molecule, and we also have two of those. So we can think of, for our reactants, what we notice is that we have two hydrogen-hydrogen bonds. We also have one oxygen-oxygen double bond. And then we go to our products, and we think, how is this going to connect back to our energies? We are going to see that we have two oxygen-hydrogen bonds for every water molecule, but we also have two water molecules. So I could think of, I have 2 moles of water, and then I have 2 moles of oxygen-hydrogen bonds in each of those moles of water. And we're counting for, basically we have a total of 1, 2, 3, 4. We have 2 moles of water that are being produced there. Each one of those has 2 moles of oxygen-hydrogen bonds. Then what we would do is we'd say, well, now we know the number of moles of hydrogen-oxygen bonds we have, the number of moles of oxygen-oxygen bonds we have, and the number of moles of hydrogen-hydrogen bonds that we have. And as we look at that, it's going to be helpful for us to identify, will those energies be different, positive or negative, when we're looking at our reactants or our products. So now that we have all this information here, let's go ahead and bring it down to here, and let's identify which bonds are actually broken and which bonds are going to be formed and the energies of those. So now if we go ahead and we continue to utilize our table here, we notice that we have 2 moles of hydrogen-hydrogen bonds, and each mole of hydrogen-hydrogen bond is going to take us 436 kilojoules per mole. Right? That's how much energy is going to be needed to break our hydrogen-hydrogen bonds. In addition to that, we also have 1 mole of oxygen-oxygen bonds. And each one of those moles of oxygen-oxygen bonds is 498 kilojoules per mole. So what we can think about here that we've written out is we can say that is the enthalpy change to break all of the bonds in our reactants. So those are all positive. Right? It's going to take energy to make that happen. Then we go ahead and we look at and we see, well, now I'm going to form, we said 4 moles of water molecules, of oxygen-hydrogen bonds in our 2 moles of water molecules. So I'm going to say, I'm going to go ahead and add to that, because we have this change, we're going from products to reactants, and the net is looking at what's happening here. I have 4 moles of oxygen-hydrogen bonds, and I'm going to show us 2 ways of possibly thinking through this. Each one of those moles of oxygen-hydrogen bond, it takes 464 kilojoules to break one of those, but we also could see it's negative 464 kilojoules per mole that is released when we form 1 mole of those. So here we're looking at adding them together, and we can see this would be negative 464 kilojoules per mole. Or if we wanted to, we can think about also maybe subtracting the amount that would have been if we were breaking those bonds. I think it's a little bit easier to conceptually think about the fact that I know that I'm going to be breaking the bonds in my reactants, which makes them positive, and I know I'm going to be forming bonds in the products, which is going to be negative. And so we go ahead and see the net change of breaking all of our hydrogen-hydrogen bonds and oxygen-oxygen double bonds and forming all of those oxygen-hydrogen bonds in our water molecules is negative 486 kilojoules. So we notice that this is an approximation for delta H, the change in enthalpy as we go from reactants to products by looking at our bond energies. Now if we go back and we look, well, the value that we actually had, the delta H that was actually had, that we were provided, is negative 483.6 kilojoules. And what we notice is these are not the same. Okay, and so we see it's important to identify the fact that this is an approximation, right? Here we are approximating the delta H from our bond energies. It's going to give us the ability to identify, are we breaking using more energy to break our bonds? Are we using more energy to form the bonds when we release them or absorb them? But again, here we're looking at the fact that we can approximate here. So right below this, we say, well, why is this different than the known delta H? So why is our approximated, which is negative 486 kilojoules, is our approximated delta H, compared to the actual delta H, which is negative 483.6 kilojoules, why are they different? And what we can think about, if we look up here, each of these bond energies that we have listed here, we're assuming that those are kind of formed or broken in what we would think of maybe like a conceptual vacuum, that there's nothing else interacting with them. There's nothing else present in that molecule, and we're just thinking about breaking those bonds. Now, the reason why we would say these are good approximations in energy is that we can say here is that each specific bond has a slightly different bond energy in each molecule. Now, why would we say that? We say that these are influenced by the other bonds in our overall larger molecule. So for example, if we have our water molecule, what we would see is that we break that oxygen-hydrogen bond, that the bond energy is influenced by the fact that we also have that other oxygen-hydrogen bond. So if it was just simply breaking an oxygen-hydrogen bond with nothing else present in that molecule, then we could be pretty confident about our bond energies. But here again, this is a really good approximation, and this difference here, this influence by these other bonds in our molecule, and it's very slightly, that is very small. So we see these are really good approximations. They give us a really good idea of what our bond energies would be and how it corresponds back to our enthalpy change. But what we notice is that they are not necessarily the same. And that is the reason why we can make this approximation as well. Now, the last thing that I want to mention as we're looking at our bond energies here and how it corresponds to the enthalpy change. So if we go back to our original bond energies that we would see here, this first line here, if we're going to separate these two lines, this would be 1370 kilojoules, and the sum of all of our 4 oxygen-hydrogen bonds is negative 1856 kilojoules. Again, this is negative. We're forming those. This would be positive, and that's because we are breaking those in our reactants. Now again, the larger the value of our energies, bond energies, the stronger or weaker the bonds that we would have, or net strength of our reactants and product bonds. So we could say overall net is that we have weaker overall bonds for our reactants and stronger overall bonds for our products. And again, the way that we can make that identification is that we are looking at the kind of absolute value of 1856 of bonds formed and 1370 energy for bonds being broken. And again, the larger the magnitude here that we would see, we could say stronger overall bond strength. And again, we're thinking about overall all of the bonds, oxygen-oxygen bonds, hydrogen-hydrogen bonds in my reactants, and then our oxygen-hydrogen bonds for our products. So we can make some observations there. So now that we've kind of talked through this reaction of hydrogen and oxygen forming water, I'm going to give us a chance to go ahead and pause and practice. So again, here we have another reaction, C2H5OH, reacting with oxygen to give us carbon dioxide and water. So what I would like for you to do is pause the video and go ahead and answer questions 3 and 4, where first we got to draw our Lewis structures, identify the number of bonds that we have, and then from there be able to calculate the bond energies, again approximate bond energies, that we would see for the amounts that we would have of our ethanol, oxygen, carbon dioxide, and water. So why don't you go ahead and pause the video and answer question 3 and 4. When you're done, come back and see kind of how I thought through it and see if we were on the right track. So now that you had a chance to draw out our Lewis structures and maybe calculate our enthalpy change and an approximation again, what we want to look at here is I've drawn out our Lewis structures for ethanol, C2H5OH, and oxygen molecules, carbon dioxide, and water. So now that once we have that, we have the ability to look at the bonds that we have present here. So we have all of these bond energies. And one thing to note here, we have this little asterisk for carbon dioxide, C double bond O, is that because carbon dioxide is this really compact, smaller molecule, we notice that it has a slightly different bond energy for the carbon-oxygen bonds than we would see for most carbon-oxygen bonds present in possibly organic molecules. So now that we've drawn our Lewis structures and been able to identify our bond energies, let's go ahead and look at how many bonds we have of each bond type. And that's going to help us approximate our enthalpy change. So first here we notice that we have 1, 2, 3, 4, 5. So it looks like we have 5 carbon-hydrogen bonds. And we notice that we have a coefficient of 1 here, so we don't have to double that or triple that or quadruple it. We also have, looks like 1 carbon-carbon double bond, single bond, excuse me. We also have 1 carbon-oxygen single bond. And we have 1 oxygen-hydrogen single bond. So that would be all of the bonds and the energy needed to break all the bonds in our ethanol here. Then we have our oxygen molecule. Again, here we see we have 3 oxygen-oxygen double bonds, and that is because we have a coefficient here of 3. And then over here we notice we got 1, 2, and then we have a coefficient of 2. So I could say it could be 2 moles times 2. So we got our 2 bonds in our carbon dioxide, and we also have 2 moles. So, or we could just say we have 4 if we want to count it that way. Carbon-oxygen double bonds. And then here we have 1, 2. So we could say we got 2 oxygen-hydrogen single bonds, but we also have a coefficient of 3. So we could, or we could say we have 6 oxygen-hydrogen single bonds. So now we notice here is that we are going to be forming our oxygen-hydrogen bonds in water, carbon-oxygen double bonds in carbon dioxide, and then we're going to be breaking, so positive, it takes energy to add energy to make that happen, our oxygen-oxygen double bonds, and then all of the bonds in our ethanol. So now if we go ahead and take that information, and we maybe think of writing this down, kind of in an equation here, what we'll notice is that we would have, again, let's think of, I'm going to call it BE for bond energy, for our reactants. So that would be, we got 5 carbon-hydrogen single bonds, so that's 414 kilojoules per mole for each of those. We have 1 carbon-carbon single bond, which is 347 kilojoules per mole. We have 1 carbon-oxygen single bond, and that carbon-oxygen single bond has a bond energy of 360 kilojoules. And we also have 1 oxygen-hydrogen single bond, so that would be 498 kilojoules per mole. So let's go ahead and make this per mole as well. So that would be the total energy needed to break all of our bonds in C2H5OH. Then we also have our 3 oxygen-oxygen double bonds. So to that, we're going to add 3 moles of our oxygen-oxygen double bonds, which is 498 kilojoules per mole. Sorry, I had a typo here. This should be 464 kilojoules per mole for our oxygen-oxygen single oxygen-hydrogen single bonds. So let's go ahead and make sure we know what each of these are. This is our carbon-hydrogen bonds. The 347 would be for our carbon-carbon single bonds. The 360 kilojoules would be for our carbon-oxygen single bond. 464 is oxygen-hydrogen single bond. And then our 409 is our oxygen-oxygen double bond. So that would be all of the bond energies needed to break all of the bonds of all of our reactants. And that would be 4,735 kilojoules. So that's the total amount of energy needed to break all of our bonds. So that would break all of the bonds in our reactants. Then we also can think, now we have all this information up here for our products here. So we can think of, now we're going to calculate the bond energy of the products. And that would be, again, 4 moles of our carbon-oxygen double bonds in carbon dioxide. So that would be 799 kilojoules per mole. And then we also have a total of 6 moles of our oxygen-hydrogen single bonds, which would be our 464 kilojoules per mole. And again, if we look at what each of these are, this is for our carbon-oxygen double bond and carbon dioxide, oxygen-hydrogen single bond in water. And so we would find that we would have a net of, and again, reminding us, if we're looking at this, this would be if we're breaking all those bonds, but we also want to remind ourselves that we're forming all these bonds. So we want to make sure that we identify that as negative, right? That's how much energy would be released when we formed all these bonds, and we would get negative 5,980 kilojoules. So now we've accounted for all of our reactant bonds, all of our product bonds, and now our last step is that we're just going to add these together. So we could say our delta H is going to be the bond energy to break all of our reactant bonds plus the bond energy that is related to forming our product bonds. And so we can say here we got positive 4,735 kilojoules to break all of our reactant bonds, and then we have negative 5,980 kilojoules in forming our product bonds. Again, this is to break the reactant bonds here that we would see here. And the net effect would be a negative 1,245 kilojoules. So we have a negative delta H, letting us know that we are going to release heat when this reaction is occurring. And as we release this heat, it's caused because we go from weaker bonds to stronger bonds, right? Again, we're looking at weaker overall, stronger overall, or the net bonds that we would see, and that would cause us to go from more energy needed, more energy released to form our bonds, less energy needed to break our bonds. So hopefully this gives us a good introduction into bond energy, how it corresponds back to our reactants and products, thinking about breaking bonds, so positive delta H, forming bonds, releasing energy, negative delta H, and the net effect of breaking our bonds and forming our bonds would be our overall delta H for the reaction.